So can you see my screen, everyone?
Yeah.
Great.
Mm-hmm.
So this week's session is about models old and new. So obviously sort of ones that are centuries or a century old were sort of standard compartmental models, and then sort of through time, stochastic and age-structured models. We've just heard about network models. I'm sure we'll hear a little bit about agent-based models from Neil, but I'm going to focus on perhaps the most recent sort of class of models, and that's phylodynamics models. So those are ones that try to integrate evolutionary models, the philo bit, with epidemiology, but perhaps also immunology, ecology, and so on, with the idea that different data streams can complement and enhance each other. There was a recent comment in Nature by Julian Villabona-Reynolds, Bill Hanage and Damien Tully, where they argued actually not only can we integrate phylogenetic data with epidemiological data, but we should in order to avoid making mistakes in our conclusions. So in terms of sequence data and SARS-CoV-2, why should we bother to include it into our models? Well, firstly, it can tell us a lot about the introduction of cases in a region, something that might be very difficult to do with classical epidemiological methods. It can give good estimates of how different areas are spatially coupled, can do so even in an endemic setting, and can also reveal some hidden heterogeneity, at least under particular circumstances, so whether there are super spreaders, etc. And there's been a remarkable generation, as well as dissemination, of sequence data from SARS coronavirus 2. GISAID, which is an initiative that was set up to share influenza data, has been collating both metadata and sequence data on coronavirus from around the world. And then there's been an amazingly active collaboration within the UK, with multiple centres doing sequencing and bioinformatics. So as of the 18th of May, the sequences that were stored in GISAID, predominantly coming from the UK, largely due to this consortium, but we have around 5,000 or so from the US, and then on the order of hundreds for other countries. So the coverage of sequence data is not ideal. Where the epidemic is the most active, we don't have lots of data. Italy, for example, Spain are not highly represented amongst this data set. But you can see that the UK has a remarkable coverage, given that we've got quite a few cases, but our sampling density is very, very good. And that's very important for making inferences from the data. If we break it down by the 4 nations, although Wales and Scotland have far fewer sequences than England, their sampling density is as good, if not better. And in terms of when those sequences in the UK were generated, sampled, there were very few throughout the first month or so of the UK epidemic, and then it's undergone sort of very rapid growth through April, and it's starting to tail off now. I'm presuming partly due to the delay in getting sequences, getting samples and sequencing them, but also perhaps in terms of new cases coming in. And it's not just that there are increased numbers of sequences, and it's that they're also very accessible. And by accessible, it's not just the ability to click a link and download those sequences, but also there's been a fair amount of processing that's been done that means that somebody with less bioinformatic expertise has fewer things to do. And also that there's a sort of common data cleaning process that's shared between people, so they're working from the same data. So the sequences are aligned, and also they're assigned lineages, which normally the way that lineages are decided, a committee gets together and decides upon what to call each clade, etc., etc. That's been done in remarkable time. It's an initiative that was led by Andrew Rambo. And so everyone can talk about the same sorts of lineages, and everyone knows what I mean. And then there's also been a number of dashboards that have displayed those data. One that was received a lot of well-deserved attention is NextStrain. NextStrain's well suited to look at very broad patterns of dissemination of coronavirus around the world. There's coronavirus glue from Glasgow, and that's very useful if you want to actually analyze your own data sets and integrate them with a database of sequences. And I'll talk a little bit more about MicroReact, which is an initiative led by David Anderson at Oxford and the Sanger, which consumes all the data that's generated by the Coronavirus Genomics UK Consortium, and then displays the lineages and the timeline of the sequences. So this represents a map of where the sequences were generated. You see that it has a fairly good distribution across Britain. In terms of the sampling, it was not great during the first month or so of the epidemic. And then in terms of lineages, there are a number of lineages. There are some that are more common than others. For example, lineage B1, which you see here in this shaded polygon, that's also the same variant that contributed a lot towards Italy. And one thing we do know is that a number of the introductions into the UK were tourists who came from Italy back into the UK, and that is consistent with that, those epidemiological observations. So despite having thousands of sequences, studies are fairly limited in terms of phylodynamics. If you look at the medRxiv, bioRxiv, and search for SAR and COVID-19, you come up with hundreds of hits, and you just have to do a cursory search of people who've been trying to model the spread of coronavirus, and you'll see that there are many, many studies, many compartmental models, etc. If you look for phylodynamics and COVID-19, you get just a handful of hits. Moreover, until recently, the sample sizes of those studies were quite small. We're still having a bit of a lag in terms of when the data are generated and when we can do analyses. And they've typically been stronger on the phylogenetic side than on the modeling. So whether you classify those as a true phylodynamic study is a moot point. There are a number of studies I'd like to pick out. One of the earliest ones is a report from Imperial led by Eric Volz, and they had a compartmental model where they had assumed heterogeneity in infectiousness. So they assumed that there were people who are highly infectious and people who are less infectious, and using this model, they fitted it to a small number of sequences, only 53, predominantly from China, and from that could estimate R0, which was reassuringly consistent with estimates that were coming out from analyses of cases and deaths. And in terms of looking at the number of infections over time, they were sort of rising at an exponential rate. So at that time, at least, there was no sign of the epidemic tailing off. Using the same model, but applying it to a more sort of self-contained and highly sampled setting, again in China, they found that the number of infections were starting to tail off, and that was consistent with what the observed infections were doing. And there was about a 10-fold or so disparity between the estimated number of infections from the phylogenetics compared to the number of known cases. And that's not entirely surprising. So this was not a joint estimation. This was just using the phylogenetic data and trying to estimate the number of infections from that. Another study that's larger, applied to over 1,000 sequences, albeit taken from multiple locations, is a study led by Lucy Lee. And in her case, she did some joint estimation looking at both cases and the phylogeny using a branching process model with time varying parameters. And because both sources of data were included, then there was the ability to estimate the extent to which cases were undercounted, as well as heterogeneity in the cases. Another study I'd like to highlight is one led by Torsten Seaman from Australia, who fitted a model in which over time the effective reproductive rate could change. And in this particular model, you could assume a sort of breakpoint where there's a sudden change in R, and they fitted that to nearly 1,000 sequences and found that R had decreased quite substantially around the 27th of March, which coincided with the time that quite aggressive movement restrictions were put in place. In addition, the timing of some of these nodes representing potential introductions into Australia was still occurring during restrictions on arrivals, but so there appeared to be quite a bit of transmission that was occurring in Australia long before the sequences actually were sampled. And that's a fairly typical observation in many phylodynamic studies, that there is some transmission long before you start to get your sequence data. The problems with many studies, but with few exceptions like the ones that I've outlined, studies that use SARS coronavirus 2 sequence data tend to be more phylogenetic and less on the modeling side, less on the dynamics. And the data sets are large and expanding rapidly. So whilst that does give us opportunities to fit more complex models, they're also much more computationally expensive and just take longer to run and to build and to troubleshoot and so on. So the solutions for that, in the longer term, we need to think more about scalable inference. How can we do these sorts of phylodynamic studies in real time? Not just display the data, but really sort of glean lots of information from it. But we're in the middle of a pandemic, and there's pressure on us to be able to come up with recommendations and insights into the data as it's generated. So in the short term, I think there are a couple of things that we could do. One is to look at smaller, such as subnational epidemics. And the second is to generate predicted phylogenies from existing models that people have generated. So don't try to do the inference or on the phylogenies, or try to do some joint inference, which is even more challenging, but just try to say, well, what does a phylogeny look like from the model that I'm fitting to case and death data? So looking at, say, subnational epidemics is reasonable. From the past, we know that analyses of data sets in the low 1000s is possible with current frameworks. And so places like Scotland and Wales, where the sequencing depth is actually quite good, could be good candidates for things, for scenarios where we can fit the suite of phylodynamic models that we already have. So here is another screenshot from MicroReact looking at the dynamics in Scotland, and you actually see that there are quite a few multiple co-circulating lineages, but still, you know, over 1,000 sequences there. And the situation in Wales is a little bit simpler in that this B1 lineage really does dominate. So if we wanted to actually scale down our inference even more, then we could focus potentially on a single lineage. But that starts to raise methodological questions of how do we generate epidemiological models where we focus in only on a single chain of transmission. especially when those chains of transmission might sort of compete in terms of herd immunity. Another thing that we can do is try to generate predicted phylogenies. And the reason for that is that algorithms and tools exist right now to take epidemiological models and output phylogeny from which you can calculate anything that you want. For differential equation models, there's a package, Phylodynamics by Eric Volz. Tim Vaughan has a package to do much the same thing, but using sort of stochastic Gillespie type models. And if you're developing an agent-based model, it's actually very straightforward to output data in a certain format and then get an external package to generate the trees for you. Matthew Hall has one that was used in the Pangea HIV study called Virus Tree Simulator, and one that we've used in our work comes from Sergei Kosakovsky Pond, which again just takes a line list of infections and recoveries and builds you a phylogeny. If you want to do that, if you want to sort of retrofit your model to generate phylogenies, you do need to understand the link between those two and actually how you do it. And that's really about trying to break your model apart into processes that contribute to the phylogeny and those that don't. So analogy here is if we're considering deterministic versus stochastic models, if you just have a, say, a birth-death process for a differential equation model, the only thing that matters is the difference between those two rates. But if we have a stochastic model, we have to consider those two rates independently because it's the absolute size of those rates as well as the difference that drives the dynamics. So it's not sufficient to have like a single equation. We've got to sort of break the model up into its constituents. So to go from an epidemiological model to one that's phylodynamic, we have to consider those processes that result in branching in the phylogeny, and that's transmission, as well as processes such as movement that can result in a change of state. So a lineage might change from one location to another. With more work, it's possible to extend models to give not just to simulate a phylogeny, but to actually generate summary statistics of phylogenies as the model's being run. That requires more methodological development, and that's something that we've worked a bit on. The nice thing about that is that it's very fast to do. You don't have to generate lots and lots of phylogenies and analyze them. You just get some estimates from the model itself. So here's an example from an old paper of ours where we were looking at an SI type model, but it had a core group. So it had a small number of individuals that had a high infection rate, and then an individual group of individuals with a lower infection rate. And then as you change the ratio of contact rates, you start to change the phylogeny. So this on the left here, a thing called cherries. These are tips that are joined to each other as they look like a pair of cherries, and they're a measure of tree structure. And as you increase the ratio of contact rates in the core group relative to the non-core group, then this statistic starts to shift. There isn't much signal in terms of seeing whether the high risk group and the low risk group actually mix together. And then here's a different measure of the tree structure. This measures overall asymmetry, and at least for sort of moderate levels of disparity in infectiousness or contact rates, there's an impact on the phylogeny. It becomes more asymmetric, although you see that this relationship is actually quite nonlinear. So there's signal in the phylogeny that can tell us about things like heterogeneity, even if we can't actually assign individuals to being in a core group or not. So that requires quite a lot of painstaking bookkeeping to do, but in terms of just generating a phylogeny, it's quite straightforward. If we take Eric Volz's package in R, we basically, this is for just an SIR type model, we have to break up our transitions into births, in this case, infections, deaths, which in this case is recovery as well as death. So these relate just to infectious cases, remembering that we can only get sequence data from those people that are infected. And then there are other dynamics that we have to consider which don't show up directly in the phylogeny, because we can't get pathogens from recovered individuals or from susceptible individuals, but they do affect the dynamics, and so indirectly impact the dynamics of infected individuals. So if we break up our SAR type model in, or particularly breaking up the dynamics for the infecteds, then what we can do is that we can recover our normal trajectory, but we can also generate a sampled phylogeny and compare that with our observed phylogeny, or calculate any statistics that we want from that. We can generate sequence data along this phylogeny if we wish. For stochastic models, there's this existing package called master. This requires that you specify the model in terms of individual reactions, just like in a chemical kinetics sort of model. And in addition, you basically have to tell the model that it should follow lineages of infected individuals. And this can be extended to infected individuals in multiple stages or locations and so on. And finally, if you're running an agent-based model, you just need to keep track of who infected whom and when infected cases die and recover. So here's like a toy example where an individual infects another individual at time 1, that individual goes on to infect another at time 1.5, and then that first individual recovers. So this is just a formatting that we've used in our package to determine that an individual is recovered rather than infects another. And this is all that you need to make a phylogeny. So it's very straightforward to generate, and this has the sufficient information you need for the packages to generate a tree where you can do the analysis that you want. In some cases, it might be easier to fit a certain type of model, say a differential equation model, and then to create a phylogeny actually sort of move to, say, an agent-based approach. So one of the things that I've done as sort of an educational and research tool is try to collate lots of different model formulations and implementations. Here's a link to one where for a given SAR model, I've tried to make different approaches to the same underlying problem using differential equations, ordinary or stochastic, using function maps, Markov models, Gillespie type simulations, agent-based models, etc. More or less, you can describe pretty much all of these using sort of a stochastic Petri net formulation. But one thing that I think it is important when we're trying to model is to be open that our model really is sort of how we've put together the pieces, and then we should perhaps separate that out from how we've tried to implement that. And that different implementations might lend themselves better to inference or forecasting or generating phylogenies than others, and we shouldn't be afraid to try to switch between those. One of the issues with SARS coronavirus 2 is that it's not that diverse, even though the genome's around 30,000 or so base pairs. It's under quite a lot of constraints. Coronaviruses have a lot of RNA secondary structure that means they don't mutate incredibly fast. And because of that, if you try to generate a phylogeny, it doesn't look very nice, even though we've got the full genomes for many of the samples. So do we need the full phylogeny, given that it does have lots of ambiguities in it? Or do sort of cruder classifications into lineages suffice? So Andrew Rambo et al. Have had developed a naming scheme for lineages, A, B, B.1, B.11, etc., that are sort of hierarchically structured. And perhaps we can just plug those into our models as a quick way to retrofit them and try to bring in some evolution into our transmission models. So this is the UK phylogeny. This is a tree from microreact again, and you see that there's lots of these fan-like structures where we don't have a nice binary tree, which is sort of an underlying assumption in many of the phylodynamic models. We're also having cases where we have what look like sampled ancestors. We're getting chains of infection where one sample looks like it's been derived from another. And again, that's not well dealt with in phylodynamic frameworks. I think in the longer term, rather than just repurpose existing models, I think there are also some ones that we can explore. I think there's still an open question of how can we represent genealogies in a forward in time epidemiological model. And there's actually been quite a lot of work in population genetics thinking about this, not in a transmission setting, but in a sort of population framework nevertheless, which are considered Fleming-Viot processes that are a type of probability measure valued processes that are forward in time, unlike the sort of coalescent processes that people use for evolutionary models. But the nice thing about that is that the population geneticists have sat down and thought a lot about how you formalize different genetic systems. So having different strains that can evolve into another, or having a long genome where mutations are unique and are then inherited. And so I'd refer you to a nice paper by Ethia and Kurtz in 1993, which is around 40 or so pages, that gives a lot of ways in which we could bring in structures of genealogies into our model. That's not going to occur this week or this month, this year even, but I think it's something that's long overdue. So to conclude, the densely sampled coronavirus 19 epidemic in the UK provides challenges and opportunities for methodological development, as well as understanding contact structure. This has been a sort of huge experiment in terms of shifting how people interact, and there's just enormous amounts of information that can be gained from that. Many existing models can be quite easily retrofitted, easily as in on the timescale of this workshop, to generate pathogen phylogenies. And I think that's going to be an important aid to model comparison, as many models through design have been trained to fit case data or death data, and so it then becomes very difficult to say whether one model is actually more realistic than another. And by branching out and looking at phylogenetics, we have a means to actually compare those models in a much richer way. So with that, I'd like to thank everyone and take any questions.
Thanks, Simon. Do you want to unshare your screen and we can, thank you. Right, so do we have any questions?
I have one to start off, perhaps. The number of sequences you have in the UK is pretty remarkable, but it's roughly 12,000, and obviously those are cases that have been diagnosed, and I think the estimate is something like 10 to 1, the undiagnosed to diagnosed ratio. How much do we know at this point about estimating the uncertainties or biases in estimating both the phylogenetics and the phylodynamics from what is effectively sampled data, but not data that are sampled in any purposive way? It's sort of a convenience sample, right? We don't know exactly who shows up and gets tested. So that's always been a kind of an open question. I think phylogenies are very much like networks in that way, where if you miss one person, you can potentially miss an important structuring element in the entire tree. So how much are people working on that at this point, trying to understand the relationship between sampling and estimation?
We've done quite a bit of work on the impact of sampling on phylogenies, and there are some sorts of sampling, for example, variable sampling rates over time, that the models, or at least some classes of models, are quite robust to. Sometimes that sampling might be informative if you have some purposive sampling such that the number of sequences you get in some way reflects the number of cases that are circulating, then that's very useful and you can pull that into your likelihood function. If you don't trust that, then a good case of that would be the HIV epidemic in the UK, where we've got lots of sequences now, but throughout the 80s and early 90s we had none. Then that's fine. I think one problem of sampling is if there's some, and this is the same for cases, if you have individuals coming from the same household and they're getting sampled and then sequenced at the same time. And people try to get over that by doing some subsampling. So they'll take sequences that are more or less identical and take only a single representative of the cluster. But ideally, you'd like to have sufficient metadata to be able to say that individuals are from the same household, or if they're children that go to the same school, or if they're elderly, that they've come from the same care home, etc. So I think it's not, if you just go to the public data, the sampling in terms of oversampling a particular subnetwork is a real problem. And I think that could be overcome if we had access to richer metadata. But until we have access to that, there isn't really the incentive to develop those methods that model the sampling process in the sort of way that you're asking for.
We had a question from John Pitchford.
So I can see the point of these models. They're excellent, but I'm wondering if you can, this diversity exists for a reason. There's some selective pressures which are either natural within the environment or which we're imposing by our response to an epidemic. And do we need to know about these processes in order for these predictive models to be useful?
For if you look at the phylogeny of SARS coronavirus 2, it looks very much like a the viruses that basically have no herd immunity. So that's so even if there is herd immunity, it probably the virus probably hasn't reached a high enough prevalence for that to really drive the evolution. So many of the mutations that are occurring are probably neutral, like many RNA viruses. This virus is operating pretty much at the edge of thermodynamic limits, and so most of those mutations really are just markers of geographic spread. There might be one or two mutations that are functionally important, and there's if you look at there's a website called hifi.org that's developed by Sergei Kokovsky-Pond, and he's been tracking the evolutionary evidence that mutations might be functionally important rather than just neutral markers, using a variety of different measures, like are they variable within an infected individual? That's a fairly good marker we've found of immune selection pressure. So to date, there's probably just one mutation that might have an impact functionally, and then the impact of that function might be drowned out by all the other variability that we have in terms of contact rates and so on. once we have an established epidemic, then things like herd immunity might kick in, and we might end up with a scenario much like influenza, where those mutations are really very, very important. But at present, in a naive epidemic, I think we're fairly safe in assuming that those mutations are just markers of the transmission pathway.
But you are inferring that there are potentially different transmissibilities or lethalities with these strains?
No,
Or
no,
not?
not at all. No, it's probably being driven more by the underlying contact network than anything else at present.
David Pascal had a question about difficulty of fitting.
Yeah, so when we're fitting one of these analyses, for instance in BEAST, and we know that as we increase the number of tips in our analysis, we're having a massive increase in the tree space and the size of the space we're looking in, and that the posterior is becoming more and more peaky. I was just wondering whether or not you thought that if we're having to do fast analyses for, essentially because we want answers, rough answers quickly rather than exact answers that might take a long time to run, should we be essentially caveating more on the basis that while it may look like a run had converged, in fact, if we'd run it for 1 billion more iterations, we might have found a better posterior peak, and how we should present results under those time-limited circumstances?
Yeah, the numerics are a really tough one, and I'm kind of hopeful that with the RAMP initiative, that people that are sort of experts in numerics can take a close look at this. So I think part of the problem is that there are very few people that are working on the underlying methodology, and you get more interest from having a cool new model than you do in making an algorithm more robust, unfortunately. I think just being open, and if your BEAST code, uploading your XML file, uploading your output, I think people at least that are aware of those issues would accept that. I don't think you need to have any more caveats than that. I think the issues start to come along when some of those results get out into the open. So there was a press release that I saw talking about some research from UCL, and their BEAST analysis had the most recent common ancestor of SARS coronavirus 2 occurring long before the beginning of December. Now that's just error bound caused by noisy data, but epidemiologically that's a huge issue. Was coronavirus circulating, in autumn in the UK? So